Everyone, my name is Sankarshana Venugopal, and this is DBMSolver, a training-free sampler that makes high-quality image-to-image translation possible and dramatically faster. This is a joint work with Mohammed Mustafavi and Jungin Choi at the Seoul National University. First of all, let me show you that DBMSolver produces unmatched quality at just 6 NFEs, as you can see over here, achieving state-of-the-art results in just 6 NFEs. So now let's start with the problem. Image-to-image translation maps one image to another in painting a masked region, turning a sketch into a handbag, or a semantic map into a face. Diffusion bridge models are DBMs. They are a really elegant way to do this. Instead of starting from a pure Gaussian noise, like standard diffusion models, they build a bridge directly between two arbitrary image distributions, exactly what translation needs. But there's a catch. They're very slow. State-of-the-art DBM samplers need over 100 network evaluations to produce a coherent image. The hybrid Hoyne sampler takes 119. That's a real barrier to using these models in practice. So why not reuse fast samplers? Because we already have them, like DDIM or DBMSolver, DBMSolver++. Well, that's because they all rest on one assumption, and that is that the starting distribution is Gaussian noise. As the table here shows, that's fine for standard models, but a diffusion bridge starts from an arbitrary image, not noise. So that assumption breaks, making those solvers produce artifacts, and they're simply not valid for bridges. So what is our co-insight then? So we went back to the math, and looking closely at it, at especially the reverse time bridge equations, we uncovered something prior work overlooked, a semilinear structure. The dynamics split into a linear term in the current image plus a nonlinear term driven by the network's prediction. That's the key. Using exponential integrators, we solve the linear term exactly in closed form, eliminating a major source of approximation error. We only ever approximate the nonlinear part. Now let's take a look at our proposed algorithm, the DBMSolver algorithm. This analysis of ours gives us a two-phase algorithm. Phase one is a single stochastic microstep at the very start using a first-order bridge SDE solution. We keep it simple here because going higher order would risk coefficient divergence and bias nothing over such a tiny interval. And phase two is the main juice of the algorithm, is where we handle every remaining steps with our exact closed form second order bridge ODE solution, and we finish with a final Euler step to produce the image. So here we use a second order bridge ODE solution, as I mentioned, but why stop at k equals 2? Why not k equals 3 or higher? Well, that is because third order and beyond run into non-elementary antiderivatives. There is no closed form solution. Methods like DBIM fall back on numerical multi-step tricks, and therefore they paradoxically increase the error bounds. Our second order solution stays analytically exact, and as the results show, that exactness wins. And here, as we can see, we have unmatched quality at 6 NFEs and unmatched quality and at even higher NFEs as well. We can see that DBIM lands at an FID of 12.13 in the table of the main paper at 6 NFEs, whereas DBMSolver gets 3.38, and this is on the diode dataset. And we can see that on the diode dataset, the tree branches and twigs are rendered cleanly for DBMSolver, whereas for DBIM, there's a lot of smoothing. So same compute budget, but DBMSolver producing much higher quality. Here we see in the complete results table that on diode, DBMSolver beats hybrid Hoyne's 119 NFE results in just 6 NFEs and the 20 NFE results of DBIM, and we reach 2.06 FID. On phase 2 comics, we again, in 20 NFEs, we reach an FID under 1. So let's take a look at the efficiency trends as well. We see that across every data set, our curve drops faster and stabilizes earlier than every other baseline. High fidelity at low cost, scaling smoothly as you add more steps. This is across 3 different data sets. And I'd like to mention once again, this is completely training free. It's a drop-in replacement. There is no training. No fine-tuning, no architectural changes required. Distillation methods like CDBM and IBMD, consistency diffusion bridge models, and inverse bridge matching distillation, they match our speed. They actually are faster, but that's only after massive retraining overhead. DBMSolver is a pure mathematical upgrade, and you can apply to any pre-trained bridge model today. So, in conclusion, by uncovering the semilinear structure of diffusion bridges and solving it exactly with exponential integrators, DBMSolver delivers the state-of-the-art image-to-image translation results in as few as 6 steps with no training required. Our code will be public. Scan the QR code or visit the link. Thanks for watching, and please come find us at our poster. Please email me if you have any other questions. Thank you, and have a good day.